Hi everybody and welcome to the next chapter in our course. So today we're going to talk about complex numbers, and what we're going to cover is a little bit of the motivation and how to introduce complex numbers, and then we'll talk about how they fit in with other number systems that you know, like the real numbers and the rational numbers. And then the bulk of the lecture is going to be focused on the graphical representation of complex numbers, what do they represent, and calculating with complex numbers. So some concepts like the modulus, the argument, the complex conjugate, and also doing arithmetic, multiplying, dividing, adding, subtracting complex numbers. So in order to understand where complex numbers come from, let's have a look at maybe a motivating example. So let's look at the following quadratic equation. We want to solve for x. The equation given by x squared minus 2x plus 2 is equal to 0. So you know how to do that. You calculate the discriminant. So it's b squared, so it's minus 2 squared minus 4 times a, which is 1, times c, which is 2. So you get 4 minus 8 is minus 4. And in particular, this is a negative number. So you've been taught up until this point that there are no real solutions. So in particular, if you draw the graph of y equal to this expression of x, you will get a parabola which lies entirely above the x-axis. But let's try and persist a little bit, and let's keep on calculating with what we have here. So if discriminant is minus 4, then we know the solutions are given by x equal to minus b plus or minus the square root of the discriminant divided by 2 times a. So that is equal to minus 2, so 2, plus or minus the square root of minus 4 divided by 2. And we just pretend that this makes sense. And another way to write this is 2 plus or minus, and now I'm going to take that 4, which is 2 squared, and take it out of the square root. So I get 2 times the square root of minus 1 divided by 2, and that simplifies to 1 plus or minus the square root of minus 1. So what we've done here is we've dragged along this negative quantity that we took the root of. We had it here, and now we have it here. And this is of course something that we can do in real arithmetic with real numbers. So let's give this a special name. Let's call this I. So in other words, what we have is that we've defined I to be the square root of minus 1, and therefore if we take the square of that, I is a number whose square is equal to minus 1. So this is a new quantity which we call the imaginary unit. And we see if we're willing to accept that this I thing makes sense, then we can solve this quadratic equation and we get two solutions, one plus or minus I, that basically makes sense just the same. So there are two conclusions that we can draw from this. So conclusion one is, if we allow I equal to minus 1, square root of that, then every quadratic equation can be solved and has two solutions. you can have one solution with multiplicity 2, but I'm going to ignore that for a second. And the second conclusion, which is maybe a bit harder, but we'll see that in the course of today, is we can calculate with I is equal to the square root of minus 1, as long as we remember that I squared is minus 1. So in particular here in the previous expression here, you see that we have the sum or the difference of a real number and an imaginary number. But that's perfectly okay. And just a little bit about terminology. As you've seen, imaginary numbers are basically any numbers that are I times a real number. So 7 times I, 2I, and so on. Those are all imaginary numbers. Historically, imaginary numbers were introduced precisely for this property. So people were solving equations and they realized, well, if we just pretend that square root of minus 1 makes sense, then we can do a lot of things that are nice on paper. And so that gave rise to complex numbers as a way to calculate. And then later on in mathematics, people studied complex numbers and other number systems for their own right. So they really make good sense, even though at first sight they look a bit imaginary. So let's review the number systems that we already know, and let's see where the complex numbers fit in. So the first set of numbers that you know is called n, which is basically the set of natural numbers, 1, 2, 3, and so on. And these numbers, if you think back about history, they basically show up when you want to do things that involve counting. So I have 1 sheep, 2 sheep, and so on, counting. And then the next setup is denoted by z. And z is basically the set of integers. So it's all the negative numbers, minus 2, minus 1, 0, and all the positive numbers, 1, 2, 3, and so on. So these are the integers, and they basically come up when you do adding and subtracting. So in the early history, people realized that you don't just want to count, but you also want to be able to talk about negative quantities. For instance, if you want to say, well, I have so many and you give me some more, how many do I have? And then moving on from that, the next step up is if you start multiplying and especially dividing integers, then you end up with fractions, which we denote by q. So q is basically the set of all fractions m over n, where m and n are elements of the integers and n is different from 0. So this gives you fractions, and as I already mentioned, this happens when you do dividing and multiplying. So you see, every time that you want to do a new mathematical operation, you basically expand the set of numbers that you can say something about. And then last, of all the systems that we know, there's one more, the set of real numbers. So this is basically the set of fractions and the set of all so-called irrational numbers. And irrational numbers are numbers like pi, e, square root of 2, and so on. So every number that is not expressible as a fraction. And here let me also write fractions as rational numbers. And here it's maybe a bit more tricky to see how these numbers come into play, but they basically come into play when you want to take limits of sequences. So you can have a sequence of numbers that are all rational numbers, where the limit is an irrational number. So for instance, pi you can see as the limit of sequence 3, 3.1, 3.14, and so on. So each term is rational, but the limit is irrational. So real numbers allow us to take limits of sequences, and now we have one more number system to add to the mix, the set of complex numbers. So we'll denote it by capital C, like this. So it's the set of all numbers a plus I times b, where a and b are real numbers. So these are the complex numbers. And how do they arise? Well, basically, as we just saw, if you want to be able to solve arbitrary equations, then you have to admit complex numbers. So a little bit of notation before we move on. So we will often use Z, W, capital Z, W, and so on for arbitrary complex numbers. And if we have a complex number, Z, we can always write it as a real number plus I times another real number. So here, X and Y are real. And if we do that, then we call X the real part of the complex number, and Y we call the imaginary part. And we denote those two by saying Re of Z is equal to X and Mz is equal to Y. So Re just takes the real part, Im takes the imaginary part.